So my name is Shreyas and today we look at a biased version of Levinthal's paradox. So what Levinthal's paradox is that he wanted to know how the protein folding process works. So he imagined that a protein wants to reach a native state n, and that a protein does a random search to do this. That this is what he imagined. But what he found out that a random search would take a lot of time, more than the age of the universe. So the paradox was, how does a protein search for its native state in such a small time? Um well, the answer was that uh, the protein does not do a random search. The search is influenced by a bias. So what kind of bias? The bias would be because of the local interactions between atoms and also the surroundings. Because um, a state would not want to go from a stable state to an unstable state. That would require more energy, and this is where the bias comes into picture. The protein would be less probable to go from a stable state to an unstable state. This is what Levinthal did not consider. So we'll look at a model which is a modified version of Levinthal's model, and we'll introduce that extra energy term for that bias, and yeah, we'll formulate that model. So consider a protein which consists of n plus 1 amino acids, hence the number of bonds would be n. And consider that each bond has some amount of stable uh, conformers, but we can classify each bond to be either in the conformer that the native state would be in, or it would not. So basically a bond can be either incorrectly placed or correctly placed. So that would be so a bond that is correctly placed, that is, it is in the state that would be in the native state. Let that be represented by C. Then the incorrect one would be represented by I. Hence, a protein would look something like this. So what we want is the native state in which all the bonds are C's. So let's define S as the number of incorrectly placed bonds. And let's define another term which is known as the first passage time, which is the time to go from some arbitrary initial S to S equal to 0, which is the native state. And let tau S be the mean first passage time, which is the average first passage time over all the pathways from that initial S to S equal to 0. So now we have this model, and let's see what this mean first passage time turns out to be. This mean first passage time is the time, we can consider it as the time that the protein requires to fold. So let's consider that the rate of correctly placed bonds changing to incorrectly placed bonds is k naught, and the opposite rate is k1. So using all of this, we get the expression for mean first passage time as this right here. How we got this, we would cover that, we'll come to that, but let's explore this equation a bit more. So instead of writing this in terms of k0 and k1, we can actually write it in terms of an equilibrium constant. Why, we'll get to in a minute. So if we write the equation of C's changing to I, the formation of C would be, the rate of formation of C would be equal to minus k0 fraction of C plus k1 fraction of I. This is the rate of formation, this is the fraction of C. So, and we know that the sum of both these terms is equal to 1 because they're fractions. And so let's consider the equilibrium constant to be equal to the fraction at the fraction of incorrectly placed bonds at equilibrium upon the fraction of incorrectly placed bonds at the correctly placed bonds at equilibrium, which is the forward rate upon backward rate, which is k. So we got the equilibrium constant here in terms of k0 and k1. And of course, using these two equations, we can write the equilibrium fractions in terms of k. But so here, using statistical mechanics, we can actually write an expression for the equilibrium constant. So consider that the total kinds of bonds are v plus 1. This includes the correctly placed and incorrectly placed bonds. So out of these, there is only one correctly placed bond, and the rest of the V bonds are the incorrectly placed ones. Here now we are going to introduce a term for the bias. So consider that the bond energy of an incorrect bond a correct bond is some epsilon. But now the energy for the incorrect bond is epsilon plus u, and this u is the correction term. So using statistical mechanics, we can find that the value of equilibrium constant will be this expression right here. And so as you can see, the equilibrium constant decreases exponentially as u increases. Which is another way of saying that the incorrect bonds would be formed less if the bias term increased. Let's consider the case when u is equal to 0. What that means is we didn't introduce a bias, and this would lead to the exact same case that Levinthal imagined. V plus 1 raised to n is the number of possible configurations, and this term is the sampling rate. So the value of this would be an extremely large thing. But since we introduced a bias term, that value would decrease exponentially with that bias term. And here is a sample graph plotted for for these values. So as you can see that the value goes to as low as 1 second for u by kt equal to 2, and even lower after that. The values for k1 and k0 have been approximated, but changing these values also would not result in a very dramatic change in the mean first passage time. So yeah, this is the graph of the mean first passage time versus u by kt. So we saw how dramatically the mean first passage time decreases when we introduce a bias term, and hence we showed how using a bias term we can get so much more closer to reality, and Levinthal's paradox becomes kind of irrelevant now because he didn't consider these bias terms. So now coming to the expression, coming back to the expression of this mean first passage time, how did we get that? Let's derive that. So let's define the rate of s going from s to s plus 1. Remember that this is the number of incorrect bonds. This rate will be the number of correctly placed bonds into k0, which is the rate of the correctly placed bonds changing to incorrectly placed ones, and the opposite rate would be this. So let's define another term here, that is p of s comma t, which is the probability that at time t the protein would have s incorrect bonds. So this rate of change of that p s comma t is our master equation that governs the time. And so we can to go further, we can apply the boundary conditions that a probability of having -1 incorrect bonds and n plus 1 incorrect bonds is 0, because we are only considering the bonds from 1 to n. So using those boundary conditions, we get this expression for mean first passage time. And to solve this further, we can use some more boundary conditions. So the mean first passage time for that is tau of 0 would just be 0, because if you so what does s equal to 0 mean? It's the native state. So if you already have the native state, the time required to reach the native state would be 0. So that is one boundary condition. And the other one is that you never require tau of n plus 1, because you are only considering s is equal to 1 to n. So that is another boundary condition, and using that and some appropriate substitutions, you get this expression for tau of s. And this can be further simplified with substitutions. And finally, on solving this integral, you get the expression for mean first passage time as this. So so all of these terms, so this expression is only when n is a very large value. So when n is very large, these terms would actually be negligible, and hence you would be left with only the 1, and hence your mean first passage time would be this expression which we saw earlier. So yeah, that's how the derivation goes. And yeah, just to recap, we saw how a biased model which favors stable states more than unstable states made a difference of almost 10 raised to 30 years in the mean first passage time. And now we know that due to local interactions, the protein manages to search its native state in a very short amount of time, because it has this bias. Thank you.